My name is Marcus. I work for Spotify security team, and I'm here today to talk about how we can analyze volatile memory on a Google Kubernetes Engine node. So this is the quick introduction for myself. I work as a detection engineer at the Spotify team. I'm a big hiker, folk dancer, and traveler. Like to do rock climbing. One of my secret skills that I was asked to put here is that I like to mimic accents, something that drove my mother insane when I was a child, and something that I still do. So if you hear me do it, just tap me on my shoulder and I'll try to restrain myself. Quick disclaimer here. As I said, I work as a detection engineer, so I'm not a kernel or Kubernetes expert. So some of the things I will show you here today is part of my own work at the company. And I hope this can provide some value for how we can analyze memory in GC and GKE nodes. And if you have other people here in the room, I think that would be great to add to that conversation as well. So feel free to ask questions, speak up, and let's make this a joint conversation. Everybody happy? All good? Okay, let's take it away. So quick agenda. So I'm going to start off with a quick summary or too long didn't read type thing, just to make sure we're all on the same page of what this talk is going to be about. I will then cover some of the things about how we at Spotify manage container workloads, and then do a high-level introduction to Google Kubernetes Engine, or GKE. Then talking a little bit about the kernel and why that's interesting for this use case. And then ending with what are memory snapshots and how can we use them on GKE nodes using open source tools, which is part of what I built together. And I'm going to end the talk with a demo. I'm going to also publish some of that code for later, so you can all take part of that if you want to. And yeah, that's the journey. And I know I'm the only guy left before lunch, and I know you're all tired after all the good talks. So I'm going to try to make this a bit energetic so we all feel a bit enlightened, and then we can head off and have some good food together. So, quick agenda. So, what is the summary then of this talk? So, the only thing I want you to take away from this talk today is basically how we can access volatile memory on a GKE node, which I'm going to show you how we can do. I'm going to do that using 3 open source tools called Volatility3, Dwarf2JSON, and AVML. And combining these tools together using a script that I built and spinning up infrastructure using Terraform, I'm going to show you how we can analyze all the running processes and memory on a live GKE node in Google Cloud. So let's talk about how we manage container workloads at Spotify. We are a big company, and we are very much involved in running our infrastructure in GCP. We operate in more than 5 GCP regions across the globe. We run up to 4,096 nodes per cluster, and we have hundreds of production clusters running simultaneously every day. We have more than 4,000 services that are live in production, spanning more than 3,000 namespaces. And providing that all together is what builds our services to our customers. So taking it from there to Google Kubernetes Engine, can I see a show of hands? How many people in here have worked with Kubernetes or GKE overall? Perfect. This is a great crowd. How many work with that, say, on a daily basis in production environments? Oh, still a lot of good hands. Perfect. So just to kind of level set this a little bit and make sure we're all on the same page, I'm just going to do a high-level exemplification here of the vocabulary that I'm going to be talking about. So for those of you who are familiar with this already, there's no news. But for the rest of us, when we talk about these things in GKE, we have, for the beginning, a cluster. So a cluster spans a lot of different nodes, where a node is basically a cloud instance running. So one cluster, multiple nodes running that. So apart from the nodes, which are the actual cloud VMs, each of those nodes can have several namespaces where the production load is running. Now, a namespace is a way to isolate resources so that you have segmentation between the production environment as it's running on the same node. So on the same node, you can have multiple namespaces with multiple resources running in parallel, but you still have that segmentation and isolation. Now, on each node, we have one or more pods, which is the smallest amount of resource we have for an application. Each pod can contain one or more containers, where a container is basically the executable image of all the software we need to run our application. And you can have one or more pods and one or more containers for each pod that are running simultaneously in these different namespaces. So showing you a high-level picture here of what a GKE cluster looks like, we as the users and operators of the production environment will be accessing these clusters using kubectl, which is basically a wrapper for the API server. Now, in order to manage these nodes across the clusters, each of these nodes need to have a control plane in place for us to interact with and level set, so we have that interaction. Now, that control plane, together with the API server, basically controls the resources that are running on that cluster, scheduling the different pods for the production environment, making sure they are running as they should, and also keeping track of how much storage is being used, how much memory, how much CPU, etc. So that control plane is basically our brain for understanding and managing our GKE environment. Now, we mentioned that in a cluster, we have one or more nodes which can run one or more pods with one or more containers inside of them. So with that segmentation, we have all of those running as part of our production environment and interacting with the standardized Google Cloud services, such as VPC networking, disk, load balancing, and other cloud operations that a cluster needs to get access to the outside world and to manage our infrastructure. And as you see at the low level here with the labels, some of that is managed by us as operators of the infrastructure, and other parts of that, as here marked in green, is managed by Google themselves. So with that high-level understanding of Kubernetes and how that works in GKE, let's move into the next section. What is the kernel? And why would we talk about the kernel in this case? How many is familiar with a kernel definition, by the way? Cool. I have not asked ChatGPT what the kernel definition is. So I'm going to use a different analogy here, but I'm sure we could have tied that more into the talk afterwards as well and see what ChatGPT would have given us. So at a high level, and to summarize, a kernel is basically the interaction with our application and the underlying hardware. So in order for any application to work, it needs access to storage, network, CPU, RAM, all those things, which is on the backbone of that infrastructure that the application is running on. So essentially, the kernel provides all of that intermediate layer to make sure that our application is running as it should on the underlying hardware using system calls. So if that is the purpose of the kernel, why is this important or interesting? So if we can understand and get an insight into what is happening inside of the kernel, we can essentially understand what's happening across that entire infrastructure. So we can see all the processes that are running, we can see all of the underlying file systems that it's being interacted with, and we get basically that really interesting glance into that infrastructure for what it looks like and what production environment is running. Moving from the kernel to talking about memory snapshots then. So what problem are we then trying to solve with this? What is the purpose? So essentially, one of these problems that we find that are interesting, and we have production tools for monitoring this today, is how do we know what a user did after they accessed a container? So we might have some understanding from the logs. We might do, say, disk snapshots or look at network traffic, but we can also have that extra-additional insight into what the user did and what processes were running before or after a user accessed a container. So that's essentially what we're trying to solve. And as the picture here shows, I'm sure all of us in here, or at least some, has been in that position where like, yeah, something weird happened. Here's a bunch of logs. Go search through all of this. I see some of you are nodding. I've been there myself and my colleagues as well. So this is where that additional insight of using memory snapshots can become interesting. Now, it's important to say that the approach I'm going to show you here today using open source tools and using memory snapshots is one way to get that additional insight into a GKE node. Now, there are production tools available that are running this already today where you have streaming telemetry. And if you're already using those, I would say that's fantastic, and you should keep using these. This method I'm going to show you here is providing an alternative approach using open source tools, which you can use for comparison. So with this problem in mind, or what we're trying to solve, how does memory snapshots then help? So why would we then take a memory snapshot? So a memory snapshot, just like the name sort of indicates, would be one way to have a photographic piece of what was happening at a specific time on a specific infrastructure or server. That insight, together with other insights like the disk and the network activity and the logs, can give us and paint that full picture of the puzzle of what was happening at a certain point in time after a user did some type of activity. How then can we get memory snapshots? Well, this depends largely on the tools available. There's a lot of them out there, but it also depends on what type of infrastructure that you're running and what you aim to do. So in the GKE case, which is running COS, which is Container Optimized OS, you could not, for example, use kernel modules because you cannot build them from the source inside of the GKE node itself. So if you have, say, a different server where you can have a kernel module, that could be a great way to get that memory snapshots. But in other cases, you need to rely on different methods. And the one I'm going to show you here is proven to work quite well for GKE nodes. So are memory snapshots still a thing, right? Isn't streaming telemetry a lot better? I would say it is. But still, memory snapshots can be a very good complement to that additional data. Memory snapshots are still being taught by a lot of the courses around the world using different tools at disposal. So I would say it's definitely a thing, and it's more about how you use them together with your other tools in your tool stack, basically. So in summary, what are the use cases for taking a memory snapshot on a GKE node? I would say it's a couple of ones. So first of all, if you have no other solution in place to analyze volatile memory, this method that I'm going to show you here can provide that type of insight. Again, if you have other commercial tools to monitor containerized workloads, perfect. Keep using them, use this as a complement, if you will, and have that additional insight. Another use case would be for portability. So in this case, the format I'm using is called Lime format, which is open source and portable. So you can use different tools to analyze the memory dump once you actually have it. In this demo, I'm going to do a showcase of Volatility 3, but the same format applies for other tools as well. So the third one would be also if this is a single exercise. So let's say you would like to have some type of troubleshooting or extra understanding at a single point in time of what is happening on your GKE infrastructure. So you might not want to deploy a complete tool set across your entire environment, but say like, oh, this GKE node here is behaving a bit weird. I would like to understand what is running on that at a given point in time. For that, this could be an interesting one. And lastly, as I was sort of highlighting as well, if you have other tools available, this method could be good for comparison or for troubleshooting. And what that will look like, I'm going to show you in a bit. So we talked a little bit about how we can create memory snapshots using the different tools. Now, for GKE specifically, there's a couple of constraints we need to be aware of. So in summary, in order for us to do this, we're going to need three things. We need to access kernel live memory and get a dump of that. And for this purpose, I'm going to be using a tool called AVML that was originally written and built by Microsoft, but is today open source. Secondly, once we have the kernel memory dump, we need to build a symbol file to interpret that memory dump so we can understand what is actually happening inside. In order to do that, we need a VM Linux file, which is essentially the unencrypted binary of the kernel itself. So that is basically our map to understand what is happening inside of the kernel using the kernel memory dump that we have. Step 3, we're going to put all of this together using a tool called Volatility 3. Anybody in the audience worked with that tool before? Cool, a couple of hands. And taking all this combined, we're then going to be able to understand what is happening inside of a GKE node. So how do we do this? So first of all, if we have the memory dump, how do we get access to that? So in this case, what we can do is we can access this part of the file system under proc/kcore. So what is that? Basically, it's a file that represents the whole physical memory of the node that is running. And it's in the ELF core file format. So the length of that file is basically the corresponding physical RAM size plus an additional 4 kilobytes. Now, with that in mind, I'm sure you understand that if you're running a large production node with a lot of RAM on it, these dumps are going to be sort of big, which is why, in this case, AVML, kindly enough, provides also a compressed format. So we don't need to dump the whole thing. We can dump it in a compressed format for later analysis. So how do we get access to this file system? As I'm sure some of you know, you're not supposed to access a host file system from inside of a container, right? That's pretty bad. So what we're going to be doing is that we're going to deploy a custom privileged container with access to that file system on the GK node. Once the dump is complete, we can remove that container, and it's only live on that node during the time of when that memory dump is being carried out. What I'm showing you here as part of the picture is the definition of that privileged container using Terraform, which is what I'm using to spinning up the infrastructure for my demo. So we talked about getting the kernel dump and getting access to that. Step 2, we need to interpret that memory dump as well. So the easiest way to do that is using a tool called dwarf2json, where we can build a symbol file using the VM Linux file, which what I mentioned is the unencrypted binary of the kernel itself, right? Now, how do we get access to that? That's a tricky one. Has anybody worked inside of a GK node and tried to find this file any time? Anybody tried to do that? No hands, okay. It's actually present on the host file system, but it's not the accurate one. It's not the complete one. So if you try to build a symbol file using that, it's not going to give you a correct interpretation of the kernel. But what we can do instead, and this is one of the things I found when I was doing this research, is that since we know that all of the GKE nodes are running COS, there's a standard for that image, and there's a standard for that kernel itself. So if we know this is how COS is being used, could we find which kernel was used to build that image? And it turns out that we can. So if you look really closely, and I'm showing you here the screenshot from my own GCP environment, if you look at the build name for the image, there's a section in there that actually discloses the build ID of the COS that is running on that GK node. So now that we know the build ID and we know which version of COS that is running on the GKE node, it turns out there's an actual way to access the VM Linux file. This part was quite tricky, and I had a lot of interactions with some great people at Google around this. And it turns out there's an actual open API that you can use if you have the build ID to access the raw VM Linux file. I haven't found it documented anywhere, so I don't know how public this is. I have talked to said Googlers, and I have the permission to say this here today, which is good. Yeah, it's there. Like, if you know where to go and find it, you can actually pull down the VM Linux files on any COS instance that you have running, knowing the build ID. And since Google is kind enough to disclose the build ID in the image name, we now have a way to pivot from the node to the COS build ID version to the VM Linux file. And thanks to that, we can get that file, and now we can build a symbol file of that entire kernel that is running on our GKE node. That's pretty cool. So the testing setup that I'm planning to using here today, what does that look like? So using Terraform, I'm defining my resources in a GCP project. I have a single cluster running in the US West 1 region. It's running on one single GKE node with a couple of different pods associated with it. These pods are running in different namespaces to make sure we have isolation between them. And 2 pods here for the demo purposes are specifically interesting. One of these pods is called the attacker pod, or operating from the attacker namespace. It's nothing more than a custom-built Docker image that I have where I've deployed some of the tools I want to use inside of it. And what we're going to do is that we're going to be accessing that attacker pod here on the demo and run a series of commands and other things inside of that to mimic a malicious intent. Secondly, we have another pod which also is built on top of a custom Docker container that has AVML installed together with some other tools in order to access the memory dump. Now, if you remember, I showed in one of the previous slides that this pod, the AVML pod, is the privileged one. So this one has access to the host file system and can so access the kernel space, which is what we need in order to get that memory dump. Now, since we also know what the name is of this GKE node, we can pivot from that name to the image that the node is running. And from that image and build ID, we can get the VM Linux version. So putting those two together, we have the information we need to get that out and then start analyzing that. So for the demo purpose, I have a Python script that connects first to the attacker container. It runs a certain number of commands. I'm going to be doing some live commands here as well on screen. It then accesses the AVML pod and runs a memory dump of the kernel space, which it then uploads to a GCS cloud storage bucket. From there, we have a forensic compute engine, which is connected to also by the same Python script that is pulling down the memory dump. It then queries the Google API to get the code's build ID, and it downloads the VM Linux file from the open public API that I was showing in the previous slide. So with all of that together, we can then run that analysis on the forensic engine using these three things. Let's do a demo. And let's pray to the demo gods. Anybody in here had a failed demo before? Lovely. We're all in the good company here then. Cool. I'm going to be jumping out of here a bit and into my terminal. Can everybody see that text okay? Is that big enough, or should I make it bigger? A little bigger? We're going to be out of screen soon. Is that okay? Thumbs up? Everybody in the back too? Cool. Let's make the same one for this. Perfect. So what I'm going to be using first is that I'm going to access the kubectl command and then access the attacker pod that I have. So people who know and work with kubectl before, I've already set up my credentials, so I have access to the pod using my GCP principal. And now what you see here on screen is that I'm inside of that pod running on the GK node that I want to analyze. If I run a quick ls, you will see I have a couple of scripts here, one Python script and one bash script. And this pod is now started from the get-go, so it hasn't done any activity before. And it's basically, if we take, just to copy the history here real quick, we can see that we don't have much in bash history either. So what we're going to do now is that we're going to run this script called actions.sh. And what that does is that it's a few simple commands that I'm running interactively. As some of you know, if you don't have the interactive setting, the bash scripts don't log to history by default. So in order for us to populate the history here a bit and actually see a bit of actions, this is why I've set up this script in this way, where I have a couple of different commands that I'm going to be running. So if we take that out and then we check what are the running processes here as of now, we don't have much. We have a couple of things here. This image is based on Nginx, I should say, which is why you can see that activity right here. But other than that, it's not much happening. So let's go ahead and run this command script right here and see if something happened to our processes. So now we see a new active one here, which is basically a watch command that I've set up to pivot using curl to get the current IP of this GK node. So this one is just pivoting out and saying like, hey, who am I? What is this? And it continues to do that. Again, checking history, we don't have all the new commands applied yet because we're still in the active shell. If we jump out and back in again, we should see shit story. That's a new one, right? If anybody wants to do a pull request for that, I'll be in major support. So now you can see the commands that was inside of the script that have now been added to the bash history. So we have some commands being run. We have the new process, thanks to watch this active. Now let's do an additional one. So I also have mentioned I have a Python script here, and this one is quite long, so I'm not going to explain right now what it does. But as we run the Python script from outside, we're also going to be seeing this script being active. And I will ask you what you think the script does. So we're active inside of the attacker pod. Let's run the memory dump and see what we can find out. So what this script does is a couple of things. It first creates a pre-signed URL that we're going to be using to upload the memory dump to the GCH bucket. That is only active for a few hours in order for this to run. I then access the attacker pod where I run the script that you saw me mentioning before. And I'm basically dumping all of the output, so we don't have to take that into consideration. Now, if you see here, I exited the attacker pod and I went back into the AVML pod, where I am now running the memory dump using AVML. This takes quite a bit of time, depending on how large your node is, and also the difference, how the size of the memory dump will also differ. So I run this in our production cluster as a test. And in here, I'm using an isolated GCP product for the demo. Usually, it lands somewhere between 800 megs and 30 gigabytes, depending on the node level. But of course, as we mentioned, since it depends on the proc/kcore format, which again depends on the RAM and the activity, there's some consideration here that I'm going to get back to what you need to think about if you want to run this in production. So the memory dump finished, and just to make this one a little bit quicker, as the script here finished, I'm going to cheat a little bit, and I'm going to go and jump into the forensic engine and show you a test that I ran this morning to make this a little bit faster. So as you can see, this one is currently being run and active. So if we take a look at the output from one of the previous tests, we're going to see a couple of things. So I'm going to do this, and let's go into this one. So basically what we have done then using the script is that after we get the memory dump, we're going to decompress that inside of the forensic engine. Now, I mentioned also that thanks to the COS version and the build ID, we can get the VM Linux file and build a symbol file, which is also happening in the back here. So down here in the script, you can see that I now accessed the API endpoint, I get the VM Linux file, and then thanks to the work2JSON, I'm now building the symbol file using that. Up here, all of that has already happened. And I have also run the analysis on the memory dump using volatility3, and here are some of the examples that came out. So for those of you who have worked with volatility3 before, you know volatility3 has a lot of different plugins that it's using to basically get things like the process tree, the current idle files being mapped to processes, what modules are being loaded at this time, etc. So just to let this one finish for a bit, and we're going to see a similar result, but to get the summary, I'm going to jump back into my slides and show you what we can find. So let's say that we have now succeeded, and this little guy here is happy. This is a video I recorded if we would not be praised by the demo gods. So thankfully we were. So in summary then, what have we done? We have done a memory dump from the proc/kcore file in the on the GK node host file system. We have obtained the VM Linux file and built a symbol file using the work2JSON. And we now have all of the components needed in order for us to analyze this using volatility3. So if we run this using volatility3, what are we going to see, actually? So remember, we had a GK node with several pods in several namespaces that are all running on a production node, isolated from each other. So a couple of things here. So first of all, we're going to see the bash history from inside of the attacker container. Now, this is using the bash history plugin from volatility3. And although this on here shows some of the commands that you will recognize from the script that I ran inside of the attacker pod, this module or plugin from volatility3 is very tricky, I would say. I've done this test in a couple of different combinations, probably 50 times. And it's really hard to get the complete bash history. So I don't know if anybody in here is a good expert on how the bash plugin works under the hood, but it seems like there's a lot of dependencies on what commands did you run, were they interactive, did you exit the shell or enter the shell before you ran the memory dump, etc. So What you can see here on screen is the best case scenario, but I would not use this as your main source of truth to understand, oh, did somebody run a bash command? Like, did they or did they not? Because in all likelihood, if you didn't do the memory dump at the exact right time, this output here is going to be empty. So that's something really important to take away. But apart from bash history, what can we get? Well, down here, we actually have a couple of other plugins that are great. So let's start with the process list. Now, some of you will probably remember that we had the watch command being run inside the attacker pod once we had finished the script, right? And we can see that process being active here together with Python, sh, nc, and also AVML, which is all active at the same time on the production node. Anybody knows what nc is? Netcat, exactly. So pivoting from the process tree, the process list, and we get into the process tree, we can actually see some more interesting things. So if you look at this list right here, is the text big enough, by the way? Can you all see that in the back? No? Let's see if I can make that a little bit bigger. I'm going to be doing a live edit here, but hopefully it's not too bad. Nobody remembers a coward, right? Okay, is that better? Yeah? Okay, cool. So what I want to show here, and the reason is that you will see there is a hierarchical, oh, that's a long word. There's a hierarchy difference, sorry, pardon my English, between these different processes, right? So you can see that watch and Python are running on the same level, but you will also see that sh and nc are children of the Python process. So knowing that we had the script inside of the attacker container that was going to run, we can now see that, oh, this looks like to be part of that script output, right? And I can show you, or I can tell you right now, what the script actually does is that it's creating a bash script file where it downloads and then fires up an netcat listener. It then removes the file, but the process is still active, which is why you see that still in the process tree, even though the file no longer exists. So this is, again, a good example of like comparing, say, a disk image snapshot to a memory snapshot, because you wouldn't see the file there at this point, but netcat is still there and active and listening in, just like the watch command is. Now, if we come down here, and I realize this text is, again, a little too small, so I'm going to try to say, maybe I can do it something like this. Here we actually get the full process information. So not only do we see the watch command in its full, as we saw from the bash script, but we can also see how Python was being executed and the shell being active for this one called the malicious script. So in this case, the malicious script is actually the script which fires up the netcat listener and then it removes it. So you will still see it active again in the process, but the file is no longer there. And down here below, you will also see the actual netcat process being active at the same time. And last but not least, here at the bottom, we also see the AVML process being active in the other container. So again, using the memory dump at the high level here on the GKE node, we now have a full understanding of all of these processes that are being run at the same time across the different containers and pods. Apart from this example, there's a couple of really other useful things that Volatility 3 gives us. These plugins are all available and working as well in this demo, and I'm going to show you some of that in just a bit. But we can look at, for example, the mapped ELF files, we can look at the kernel modules being active, we can look at the mount points, TTY, etc. So there's some really good information in here that we can use to understand and analyze what is happening inside that GKE node. So to kind of wrap this up and summarize, we saw the running processes, we saw what they had been doing, sort of. Now, if we would not have had this at our disposal, how could we have figured out what happened, right? So as you saw in my demo, I was accessing the pod using kubectl, I was running a bunch of things, and then I exited and I came back in. So what does that look like from the log side? So as far as I know, and I might be wrong here, but there aren't ways to get the full extent of a kubectl exec command in the GK logs. The example I'm showing you here is a standardized format where you will get a log that says, oh, this user here accessed a pod using kubectl and executed something. What that is, we don't really know. Other implementation of Kubernetes offers that through the request URI, where the IP server actually discloses the exact exec command if you run that locally. If you only run, say, bin bash to get a shell, and then you run everything else interactively inside of that container, that is still going to be missing. So this is where the piece about memory dumps and analyzing the GK nodes is really interesting, because it gives us that extra context where we, from the logs, would have just said, oh, somebody did an exec. What happened after, or what did the user do? That's hard to figure out, right? Again, I'm hoping that there are more extensive formats for logging in GKE. I haven't found those myself. If anybody here knows if that logging is available, I would be happy to hear that. But from what I've seen, this is the standard logging you get if somebody accesses and executes commands inside of a container. So what have we learned? What are the lessons learned here? So a couple of things, right? So when you run something like this, there's a couple of pieces to keep in mind. So even though we define a privileged pod and container which has AVML inside of it, we need to be very mindful of the resources that that's going to use. If you remember the picture I showed you earlier in the talk about the resource controller and how the control plane is keeping managing of the clusters and the nodes, the resource utilization here is one of the key pieces. So if you, say, consume more CPU, RAM, or disk than you're allowed to, you're basically being thrown out of that node. Also, if there are resource constraints on the node itself, your pod can be rebalanced. So let's say you want to take a memory snapshot of a certain node, but as you're doing that and as you're exceeding the resources you have been assigned, your pod gets moved to a different node, which loses the purpose. So there's a real sensitivity here, how you size and scale this type of memory dump using GKE infrastructure and how your cluster operates. And some of those examples I've shown you here is what you can face if you're not careful. The other piece which is interesting is that GKE provides through the API something called a node selector. So if you want to deploy a pod, you can actually assign that through the API using the node selector to say, I want to go and assign this pod to this GKE node, which provides us with a great opportunity to deploy these custom privileged containers where we want them to be. The method I'm using here is all using open source tools. So as we talked about, AVML to do the memory dump, dwarf to JSON to build a symbol file, and then volatility-free to do the complete analysis of the process using the memory dump. Although the script and the setup I've done here is my own, anybody could go off and do this today using the knowledge in this talk. So all of these tools are available. You can implement them in any way, shape, or form you feel is applicable to your infrastructure. And as far as I know, this hasn't been done before. That's a big statement. I talked to some of the people in the Volatility-3 community, and from what I could tell from them, there's no documented way so far to do this type of analysis on GKE. So again, if you have other tools available that do streaming telemetry on GKE, perfect. But if you are already using tools like AVML for memory dumps on other Linux systems, this method is extending those capabilities to GKE to do memory snapshots. We also mentioned the public-facing API, although not documented, where you can acquire the VM Linux file if you know the build ID of the COS that is running on your GKE node. And again, lab, in this case, I was using Python and Terraform. There's endless ways to implement this using your own coding language, whatever you feel applicable, as long as you combine these 3 open source tools. Some future improvements from my side would be looking at resource calculation for your cluster. So like knowing how much resources you have on a node before deploying and scaling the privileged container to do the memory dump. So there are a couple of ways to do that, where you can see like, okay, how much storage do I have left? How much CPU do I have? and then you can size that to your privilege container so that it doesn't over-consume those resources. Automated deployments, there's a couple of ways to do this as well. There's APIs to deploy pods to certain containers, to certain nodes, using the node selector up here. And if you combine this with, for example, disk dumps or network PCAPs, that should give some really good puzzle pieces together for what is happening on your GKE infrastructure. That was all I had. If you want to get in touch, here's my contact information, and I also published this code this morning on GitHub. So feel free to go there and download it and try it out yourself. I should say it's still in the early stages, so I'm going to be making improvements to that. So if you find any mistakes on my part, let me know and I'll fix that. But everything I did in this talk, you can do as well using the code in this GitHub repository. Thank you, and I'm happy to take your questions. We have a question. I can't see who went first, but like, let's do you in the front and then one in the back. Right, so I'm going to try to repeat the question and let me know if I got it right. So the question was if I consider to automate this process and also to shut down the GKE node if it turns out we find malicious purpose. So we're not using this in production for this right now. I would say there are a couple of great ways you could do that. Also, I would say you would be very mindful before shutting down nodes in say, a production environment. But basically, the APIs for this are available. So like you could automate this using a SOAR platform or something else. Again, I'm using Python code to make it distributed so anybody could use it. But basically, using the APIs, you can do the exact same thing and connect both to the forensic instance to run the analysis. And then if you find, say, certain artifacts or certain indicators that you're like, oh, this is weird, let's terminate the instance and do additional analysis, you could automate that as well using the Google API. So we haven't done it, but it's definitely possible. And then we had a question in the back. Exactly. So I'll try to repeat the question and let me know if I got it. So the question was if we would get additional context or if it would be easier to SSH to the instance itself and then run the same thing. Was that the question? Yeah, okay, cool. That is very true, and that's far easier. So let's say if you have a service account or something else that allows you SSH connectivity to the GKE node, that would, of course, give you access to the host file system right away. We at Spotify don't allow that in production at all. So there's no way you can, using SSH, get access to our production nodes, which is why I took this format and I was using this approach right here, where you have the pod, which is privileged, would then removed once you finish. But you're totally right. You could do the exact same thing if you have SSH access. I know this is before lunch. Any more questions? Otherwise, I'm going to let you all go. One more question?
Yeah, just one question. So the process looks great for targeted analysis. If you have any idea how to do, you know, hunting on enterprise level.
So let's see if I got a question right. So like, this is a very targeted approach, as you said, right? But if I had considered a more enterprise-wide approach, or
Yeah, like threat hunting across enterprise.
right. So I would say if you would like to do this at a broader scale, so not for a specific GKE node, you probably should consider some of the tools that are available at scale for like telemetry. So there are things like, you know, Sysdig, Capsulate that monitors your container workloads at scale. This one is more targeted because, well, first of all, you could run this, let's say, for more nodes in parallel, but that is not going to be really feasible. So for that type of approach, I would say you should probably consider something which is enterprise-wide in terms of telemetry. And then you could still do this as a very focused exercise if you get a certain indicator or something that says, oh, this specific node is weird, but you still have the telemetry for your entire GKE space. So sort of answering the question like this. Okay, cool. Okay, I want to say thank you all for listening, and I will say I also have a great team from Spotify here today, and it's thanks to those great people and my girlfriend as well that I've been able to do this. So thank you to them, and thank you to you all.